Okay, welcome to lecture. Get everybody in here. There we go. All right, sorry about that. I think I posted the lab link twice, but that's okay. We're here. Right? So it looks like everybody's here. Okay, we're gonna be picking up. Although I went to the lecture one and like nobody's there, so that's not good. All right, so we're going to be picking up kind of where we left off. We're kind of right in the middle of titrations, and we started talking about some different types of titrations. We started out talking about a titration of a strong acid with a strong base, and in a titration of a strong acid and a strong base. We really sort of in all these titration curves we're going to be talking about and can kind of continue talking about, we kind of talk about really kind of 4 points along the way, or 4 sort of positions along the way in a titration curve. The one we're looking at the screen is the weak acid strong base that we finished up on, but the strong acid strong base looks very similar to that. They typically do have this S curve associated with it. And in the case of the strong acid strong base, as we talked about, we would be adding the base in that case to the acid. And before we start the titration, before any base is added, we pretty much are just left with a strong acid, which means if we want the pH of that solution before we start the titration, we really simply just need to basically go right into the pH equation. Again, because it's a strong acid, it's going to completely dissociate. And when it completely dissociates, that's going to allow you to obviously figure out the H plus concentration. And then, like I said, pretty much right into that pH equation. Once we start titrating and adding some base to that strong acid, we are going to get a chemical reaction. So as we've been talking about with buffers, as we talked about here with titrations, because we're continuously adding volume, we do want to make sure that we do sort of everything in moles, as those do remain the same. And the molarity does change. So you do need to do an ice table after you start adding. Really, the purpose of that ice table is because you're before the equivalence point, pretty much the strong base is going to be the limiting reagent, and it's going to get completely used up. So by doing that ice table, what that's really going to kind of tell you is what is the concentration of your strong acid after you added some of that strong base to it. Once you do the initial ice table there in moles, you can convert the moles back to molarity by using the total volume. So that would be what you started with, say, in the beaker or the flask, and obviously how much strong base in that case you added. And at that point, you're still left with really just a strong acid, which means at that point you could go into the pH equation as well. Then we get to the equivalence point, which is that vertical process as you're going through that sort of curve there. It goes really vertical to the equivalence point. We typically do see a jump in pH to the equivalence point. Then we typically see kind of a jump in pH after the equivalence point. As we sort of talked about the other day, as we're reaching that equivalence point, as we're getting near the equivalence point, we're almost at sort of that tipping point where we really don't have a lot of acid left to sort of handle all that base that's coming in. So it doesn't take a lot of volume to change the pH a lot. And again, that's why we typically do see that vertical rise. And again, when you look at a titration curve and you see that vertical rise, that again means that we are changing the pH a lot, but not really adding a lot of volume to do so. And as we talked about as well last time, that's usually why if you've ever done a titration, you very commonly hear that sort of saying of, I just added 1 drop and it went like super pink and stuff like that. And that's really because, again, as you clear that equivalence point, you're kind of tipping it to, I'm not going to really have a lot of acid left, and it's going to get a pretty big jump in pH. But what the equivalence point actually does represent, it's the point in an acid-base titration where we pretty much have equal moles of the acid and base. So if we're adding base, we've added enough base to completely use up all the acid we started with. And in the case of a strong acid, strong base titration, what that's essentially going to mean is we will be left with pretty much water and a salt. Now, the importance of that salt is it does come from a strong acid and a strong base. which means that the salt is basically a neutral salt. So we would expect the pH at the equivalence point of a strong acid, strong base, basically to be 7, which is why, again, it's sometimes referred to as an acid-base neutralization reaction. You're kind of left with water and a neutral salt at that point. So as we talked about, not a lot of calculation involved at that point. It pretty much should just be 7. Really don't have to do a calculation. So that's sort of the third point of the titration. The kind of fourth point is after we get past the equivalence point, which is down that top part of the curve where it sort of flattens out. And once we go past the equivalence point, again, you do need to do an ice table. Again, it does need to be in moles. And what we're going to find at this point in the titration is, since we've already hit that equivalence point, we have now kind of went over the edge there, and we're past the equivalence point, which means we have more base than acid we started with. And what that essentially does is it makes the base now the excess reagent and the acid we started with the limiting. And what that essentially means is we pretty much are just dumping a bunch of base in there. And we need to do an ice table again in moles. And the purpose of that is actually to figure out what is the concentration of the strong base that's left over at that point, because that's essentially what you would have in that point of the titration. That will allow you to get to the OH minus concentration, to the POH, and then to the pH at that point. Any questions on the strong acid, strong base titration? Okay. So sort of where we left off was right at the start here of our weak acid, strong base titration. And weak acid, strong base titration, again, is a little bit different than the strong acid, strong base titration that we just talked about. The difference is we saw at the very beginning. So I think we took a look at the very beginning here. And when we very much sort of start the titration here, essentially the only thing that we have in the beaker or flask is a weak acid. So unlike our strong acid, strong base titration, when we're doing this titration, we actually do have to do a little bit more work there up front. And I think that's what we talked about last time and kind of where we left off. So really at the very beginning, all you really have in there is a weak acid. And again, because it's a weak acid, it will require you to do an ice table. This ice table can be done in molarity because you have not added any base to it yet. So that's why we could kind of do this opening part here in molarity. Could go right in. It's basically a weak acid problem where you would do an ice table, you would use X's, and you would use the Ka value to solve for X. In that case, X would equal the H plus concentration, and that obviously would then allow you to go into the pH. Since it is an acid, it's a weak acid, we do expect obviously to be starting here in the acidic range, maybe a little bit higher than what we started with the strong acid, again, because you got that Le Chatelier's principle. It's not going to fully break apart. It's going to mainly stay together. So that was sort of the first part of the titration. So let's pick it up at this point, talking about what happens when we actually do start this type of titration. So this is from like that first drop all the way to like right before there, we hit the equivalence point would be number 2. And let's talk about sort of what is happening at that point when we're doing it. And let me just get some things on my way here so I can actually see. There we go, do that. All right, so if we're looking at number 2 here, number 2, this would be before the equivalence point. We would need to do a reaction. So in this case, we were looking at acetic acid as our acid we were starting with. Again, we're adding sodium hydroxide, which is our strong base to it. And we are going to, again, get a reaction that's going to occur. And that reaction will be basically our sodium acetate and our water in this particular case. So again, since we are adding, we do want to do this table here in moles because we're adding. And again, just to kind of show us sort of what's happening, I'm going to make up some numbers. So I'm going to start with 4 moles of acetic acid. I absolutely just made it up. It doesn't come from anywhere but my head, I suppose. Because we're at the equivalence point, again, a couple of things we should know. One thing should be this guy is like the limiting reagent in this case, which means we should have less moles than 4. Because remember, if we're at the equivalence point, then we should have the exact same amount of both of those things. So again, I'm just going to make it up and say I have 2 moles at this point. And again, we would have 0 here. Because we have not reached that equivalence point, as I just mentioned, basically our sodium hydroxide is less than what we started with. And what we started with is the excess reagent, which means the change here would be that limiting. So it'd be -2s around here in my example. That means when we reach equilibrium, we would have 2 moles of this guy, none of that guy, and we would have 2 moles of this guy. Again, as we talked about, we want to make sure we do this in moles. At this point, also very sort of important thing is to convert these things back to molarity. Again, we would want to divide by the total volume here in liters to get us our molarity of both of these guys. Any questions on the ice table setup here? So also, as I mentioned a number of times as we've been going through this, your ice table really does give you a lot of pieces of information. It's also very helpful a lot of times in case you're not sure what you got going on at this point. So if you're not sure what you have sort of happening at this point, you can look at your ice table and go, well, I got this guy still there. And I got this guy still there. Are these two things related to each other? And hopefully at this point, you'll be able to recognize that they are related to each other. That's acetic acid, that's sodium acetate, that's a weak acid and its conjugate base. That is also known as a buffer. So again, don't overlook sort of the information that's in those ice tables. They definitely can help you, especially if you're in kind of the middle of the problem, maybe you're not sure where to go next, kind of what's happening. So what does that really mean? Well, if we want the pH, and since it's a buffer, probably the easiest approach would be our good friend, the Henderson-Hasselbalch equation. Again, you probably would have the Ka value for this guy in the problem, and you could get to your pH. Your alternative could also do an ice table if you wanted to, like we talked about before, in place of the Henderson-Hasselbalch. So in this part of the titration, it is actually very different as well than our strong acid, strong base. Anywhere you kind of roll through this area is going to result in a buffer at this point. And again, it requires at least one ice table followed by the Henderson-Hasselbalch equation. Or if you're not a fan of the Henderson-Hasselbalch equation, it requires then 2 ice tables, one to get basically the components of the buffer and one to figure out what the pH is. Any questions on up to there? Okay. Then let's talk about what happens when we actually do reach that equivalence point. So let's talk about sort of the third part of the titration curve here, and we'll go there. So when we're dead there on number 3 there, which is our equivalence point. So let's see what happens here. So on that third spot there, we are at the equivalence point. And really what we should know is, again, we're going to get the same reaction occurring. And obviously we're dealing with the exact same stuff here. So a little sodium acetate and some water. Same idea. We're starting with this guy. We're adding this guy. And again, we do definitely want to do some mole action here. And I'll again start with my made up 4 moles of this guy. Now, if we're at the equivalence point, we should know that that means that the moles of the acid equals the moles of the base, which means if you're not sure, the amount of moles of sodium hydroxide in this case should be 4 moles. So a very common thing too when you're dealing with these sort of titration problems is sometimes they may not actually tell you, the volume that you need to get to the equivalence point. They may just give you the molarity, and you need to kind of figure it out. So there's a couple of ways you could figure it out. One way is if it's a one-to-one relationship between these two guys, you can actually use like the dilution equation to figure out the volume you would need to reach the equivalence point. If it's not a one-to-one relationship, you probably shouldn't use that because you'll get the wrong one because you won't have the right stoichiometry. You need to do a stoichiometry problem to figure it out. So there's a lot of ways as well. Even your ice table could help you if you're not sure what the volume is to get there, especially if you know you're at the equivalence point. As we just did here, you would definitely know, well, I got 4 of this guy. I should have 4 of this guy. And what you might know about the sodium hydroxide would be the molarity, which is moles per liter. So you wouldn't know that in the problem. And even if you weren't sure how to sort of do this stoichiometry part of it, you could go, well, I know I need 4 moles. So that's the mole part. So I could actually figure out the liters that I would need to get there by using just the molarity equation. So there's a number of ways you could kind of determine, how much volume we need to reach the equivalence point. Your ice table could help you. The knowledge of understanding that you should have equal moles at that point, along with the molarity of the base, for example, given to you, will allow you to get to the volume. You could also, again, one-to-one relationship, just kind of do an M1V1 equals M2V2 situation. You could just do a real stoichiometry problem, which is ultimately what all this is anyways, and get yourself there. So again, you will come across problems where they will not specifically say, hey, this is how much volume you need to get to the equivalence point. So you want to make sure you keep that sort of in mind. All right, any questions on that there? All right, so in this case, since it is the equivalence point, you really hopefully can't screw up because there's only one number. So that's got to be 4 in this case in terms of our change. That means, as we would expect at the equivalence point, we're going to zero that guy out. We're going to zero that guy out. We're going to end up with 4 moles of this. And again, very good practice at this point. Total volume. Also why it's important to be able to figure out how much you need to add to reach the equivalence point if it's not given to you. Otherwise, you will not have the right volume down here when you're converting it back to molarity. So that gets you back to molarity. First off, any questions on the ice table or anything else I've been spilling out so far? Yes. Okay. So again, it's very common. People get to this part and go, not really sure what the heck to do at this point. So again, if we look at our ice table, it shows us exactly what's left. We are only left with this guy right here. Hopefully at this point as well, you will be able to recognize that as a salt. And this is a salt that would potentially break apart into Na plus and some acetate. And when you think about salts, you should think about hydrolysis and reacting with water. So as we've talked about a number of times at this point, sodium we would not need to worry about because it's a neutral salt. But our good friend here, acetate, which we obviously know comes from this guy, which is a weak acid, would go through hydrolysis. So at this point in the titration, you actually then need to actually do a hydrolysis problem at this point. You need to take that salt. It's going to react with our guy water over here. And again, you might not know what's going to happen here. Hopefully you do, but just in case, you want to think about those things we talked about before. Well, it came from this guy, which is a weak acid, which means this is kind of like a conjugate base, which means when it reacts with water, it probably should act as a base, and it should accept that H plus over there. And when it accepts that H plus there, we are going to form acetic acid where it comes from. And we are going to produce hydroxide here. And this guy right here is the important part. As we also talked about before, without even picking up the calculator at this point, we should already know that our pH should be basic here because of that production of hydroxide. This ice table will be done with molarity. So you would take your equilibrium concentration, which is why it's important to get that final volume correct, and the molarity, and convert it to molarity. You would use your molarity from above. These guys would be some zeros. These guys would be some minuses and pluses. Obviously, here we are going to be using X and molarity minus X, X, and X. This would go into our K value, which would be our products in this case, divided by our reactants. And again, from our earlier conversations in earlier chapters, you also should recognize that because you have this here, you need to use a KB, which is probably not given to you in this problem. So you will have to use that KW relationship that we saw earlier. You would solve for X in this case. Our good friend X there is the concentration of hydroxide. And that's going to get you obviously to the POH and then to the pH. And you could clearly see here at the equivalence point in this type of titration, very, very different than laying up it's a pH of 7 like we did with the strong acid, strong base situation. Any questions on sort of what is going on in the equivalence point here in this type of titration? So at the equivalence point, again, obviously, as you can see here, you need 2 tables. You got to do 2 ice tables at this point. The first ice table really is just to get the proper concentration of the salt. The second ice table is using that concentration in a hydrolysis problem, and it should be basic always at this point. And you obviously need to use that KB rather than the Ka and get yourself to the pH. Any questions on any point there along the way?
So even though it's at the equivalence, it's turns out to be basic in these types of problems.
It does, because unlike in the strong acid, strong base, the first titration we talked about, in a strong acid, strong base, because it's a reaction of a strong acid and strong base, we end up with a salt that basically came from a strong acid and strong base, which, as we talked about with salts, basically results in a neutral salt, a pH of 7. This is different because we have the introduction here of a weak acid and strong base. So because that weak acid is reacting, it's going to produce a conjugate base that's relatively strong in the sense of hydrolysis, and that's where the acetate part comes from. The strong base still is going to produce that neutral salt, which is the sodium part of it, but it's actually the presence of that weak acid will give that sort of stronger conjugate base that when we're at equilibrium at this point, is going to want to continue to react with water. And because it wants to continue to react with water, it's going to produce more OH minus, and it's going to get you to a pH in the basic range because of that. Other questions? Was Samantha, was that you? Yeah.
Yeah. Could you explain again what you did up on the top right with the sodium hydroxide? Like
over here?
There. Yeah.
Okay. So yeah, let me just find somewhere to scribble on that. I'm gonna scribble down here. So what I was talking about with that is, for example, let's just say we started with 100 milliliters. That's a big titration of 0.5 molar, say, acetic acid, and we were going to titrate it with, we'll do 0.5 molar sodium hydroxide. Okay, and they go, well, you know, what's the pH at the equivalence point? And that's sort of all the information they give you. But you need to kind of know sort of the volume here of this guy for a couple of reasons to get you to that equivalence point. So one approach could be like we were just doing there, is you can use the reaction and so I just made up these numbers. We could figure out obviously our starting moles of our acetic acid, which in this case would be 0.05 moles. If I punch that in correct, I think I did. There we go. Now, because you know you're at the equivalence point, without even having any knowledge of how to figure out the volume or how many moles I would have, you should know that you should have the exact same number here in terms of moles. And what that would allow you to do is now you know what the moles should be and you know the molarity. So again, just using molarity as moles per liter, you now have the molarity. You also have the moles. So you can actually figure out the volume that would be needed to actually reach the equivalence point by rearranging that. And you would end up with, in this particular example, my made up example there, should be 0.1 liters of sodium hydroxide are 100 milliliters of sodium hydroxide. So what I was saying there is this is one way that, because you're at the equivalence point, even though you may not know how much volume you need to add to this guy, you do know these guys should be equal. And you can kind of back calculate to figure out, okay, now I know I need to also add 100 milliliters of this guy to reach the equivalence point. And that's one way that you can figure out, you know, the volume. And why would you need that? You would need that at the end when you convert it back to molarity, because you need the total volume, which would be 100, obviously in this case, plus the 100 of the other one I needed to add for a total volume of 200 milliliters. So that's one way you could kind of figure it out. Another way you could figure it out is by actually just doing a simple stoichiometry problem. You know, the volume and molarity of your acetic acid. You could do this little conversion here where we would do our 0.5 moles per liter of our acetic acid. So I write it out there. Liters would cancel and actually just do a stoichiometry relationship. So 1-to-1 relationship, which would give me 1 mole of acetic acid, 1 mole of sodium hydroxide. Moles of this guy would cancel, and that's going to get you my 0.05 moles of sodium hydroxide. And then you could do exactly what we just did right here to get you to it. And that's sort of the long version of, you could also use M1V1 equals M2V2 to do that, where you just simply go 100 milliliters of my acid, 0.5 molar of my acid equals 0.5 molar of my base, and V2 would be the volume of base. And if you solve for V2, gets you 100 milliliters. So this is sort of the shortcut of the true stoichiometry problem. And or you could kind of skip it and kind of do this part as well. But there's a few different ways you could actually sort of figure out the volume to reach the equivalence point. And you sometimes need to do that because you definitely need to convert it back to molarity at that point. Question on that? Okay. So also, again, important, this guy right here only works if it's a 1-to-1 relationship between the acid and base. Because this is really based off of this calculation down here, if it's not a 1-to-1 relationship, you will not have this part of the calculation right, and you will get the wrong answer. So a lot of things we deal with is a 1-to-1 relationship, but just keep that in mind. Not a 1-to-1 relationship, you will not work out right. Sometimes people call this the titration equation, but it really only works in a 1-to-1 situation. So keep that in mind as well. Other questions on that there? And again, it's a very common thing in titrations, especially when you reach the equivalence point. They don't just go, hey, this is how much volume you need to get to the equivalence point. So you got to kind of figure it out sometimes. Other questions on that part in the titration?
Can we still use the first calculation to find the volume when it's not a 1-to-1 ratio?
Yeah, you would, because again, you should have the same moles and you'll have the molarity and it should work out okay. Yeah. Because it'll be back calculated. It should be okay. Yeah. Other questions? Okay. All right. So the last part here, we're going to go after the equivalence point and see what's going on at this point in the titration. So again, that changing of the indicator doesn't deter you. you keep going past that equivalence point here. And in this particular case, we will end up with the same reaction as we've been dealing with. And again, you do need to do an ice table here, much like the other parts. And again, I'm just going to use my made up number here, which is 4 moles. Now, since we are past the equivalence point, as we talked about a number of times, we are definitely adding way too much sodium hydroxide in this case. So the amount of sodium hydroxide we're adding in this particular example should be more than what we started with. So again, I'll just make up the number, which is 6. Again, what that's going to do is do like a little switcheroo here. It's going to turn our acid into the limiting reagent, our base into the excess reagent. And again, here, just keep in mind, it's got to be the smaller number. Can't have the negative concentration, although people on exams and quizzes always want it. So keep an eye out for that. So again, here we do reach the equivalence point. Nothing of that guy. We got a couple of moles of this guy. And we got a couple, no, we got 4 moles of that guy. Just like before, we're going to convert these guys back into molarity using our total volume at this point. And again, just like normal, that would be what we added in terms of base to what we started with, obviously, in terms of our acid. So again, if you're not sure what's going on here, we could use our table to help us out. So we look at our table, we got some sodium hydroxide, we got some sodium acetate, and I got a couple of numbers. So clearly here, these two are related to each other as a buffer, and the answer is they are not related to each other. Sodium hydroxide and sodium acetate are not a partnership there, are a buffer. So again, this is a very common mistake. People see 2 numbers and go, cool, I'm going into the Henderson-Hasselbalch equation because I got 2 numbers and a formula. Why not? Let's do it that way. So let's talk about what we got going on here. We clearly have a salt here that will go through hydrolysis and produce hydroxide in sort of a base sort of function. We also have sodium hydroxide here, which is a strong base. So in comparisons of these two, between sodium hydroxide and sodium acetate, it is going to be the sodium hydroxide, the stronger base, that's going to be the major contributor in this solution of OH minus, actually. So although the acetate is still there, although the acetate is still like doing its like hydrolysis reaction, between the two, the sodium hydroxide is a much, much stronger base. It pretty much just needs to go for a swim to produce hydroxide. This guy's got to go hunt down some water and do a reaction. So what we do in this point of the titration is, because this is sort of a minor contributor, we actually ignore its contribution at this point. And that's because you can just visualize what you're doing with the titration. You're pretty much just opening it up and just dropping nothing but base in there at this point. And it's got really no acid left to handle it. So because that's a strong base, that means that should be the OH minus concentration. That then should get you to a POH, and then that should get you to a pH. So at this point in the titration, kind of similar to what we had going on in the previous titration, we're really just dumping a lot of strong base into there, which basically means we are just producing a lot of hydroxide ions. And again, at this point, you kind of think of your beaker or flask, you're just dumping in hydroxide after hydroxide after hydroxide after hydroxide, which means the concentration of hydroxide increases, the pH increases, and the H plus concentration decreases. So we do see that big jump. And that's why, you know, like I said, when we're coming in this titration, coming into that equivalence point, there's that big jump in pH to the equivalence point. Again, because we're kind of using up all of our acid there. And as we're adding that hydroxide, at some point we get a kind of a big jump. And once we hit the equivalence point, we definitely have now used up all of our hydroxide. So it doesn't take a lot of strong base to bring that hydroxide concentration up. And that's why we very quickly also see a pretty big jump in pH, because we're at this point just dumping hydroxide in there. And at some point, it will sort of level out the amount. And again, that's sort of where we're at this point. Actually, we're from here down. But it will sort of level out and we get that kind of curve that we typically will see. That's sort of the hydroxide sort of maximizes out at that point, that we don't see that big pH. Any questions on this part of the titration here? So again, 4 sort of distinct parts of this titration. Little different, obviously, than the previous one we did, where again we had sort of that strong acid, strong base. But here again, we starting with a weak acid, ice table, Ka problem. We're then going to enter into really minimum 1 ice table, followed by the Henderson-Hasselbalch in this buffering region. Going to require 2 ice tables there to figure out our salt and hydrolysis problem, followed by 1 ice table there to figure out the concentration of our strong base we're dumping in there into our POH and then into our pH. The good news is, again, all these calculations are stuff that we've done in a previous chapter and some in this chapter. So you should know how to do these calculations. The key here with titration, what gives people a really hard time is you could give them a curve like this and a problem, and they have no idea like where they're at. And you may say to yourself, why is it important to kind of know where you're at? Well, if you know where you're at before you even pick up the pen or pencil to do the problem, you actually know what type of problem you should be doing, rather than trying to jump into it and trying to figure it out on the go, which is what a lot of people do. And then they kind of run into a little situation there where, you know, they get there and not sure what to do next. So that's why it's important to sort of have an idea like, okay, I'm here in the titration. I should be doing like an ice table that's like a Ka problem, or I'm here, I need to do 2 ice tables or 1 ice table followed by the Henderson-Hasselbalch. So it just makes the calculation part a lot easier if you have a really good understanding of sort of where you are and what type of problem you should be doing at that point. Any questions on that there? So why don't we just try one here? So why don't you calculate the pH of a titration like we've been talking about we'll go with 25 milliliters of 0.1 molar acetic acid after, I don't know, let's do 23 milliliters of 0.1 molar sodium hydroxide has been added. Again, Ka value the same we've been using, 1.8 times 10 to the minus 5. All right, I want to take a few minutes, see what you come up with here. I'll do it as well. We'll talk about it. Hopefully we'll all end up at the same answer. Here. All right, so obviously if you're given this sort of problem as a sort of standalone problem, a couple of things you want to kind of think about is I definitely see, obviously we've been talking about, but you know, I do see a Ka value. So that should imply to me that, hey, I'm obviously dealing with a weak acid here, right? And I know sodium hydroxide is a strong base. So right off the bat, you should know weak acid and strong base titration, like we've been talking about, is sort of what we're dealing with. So we do want to know, we obviously started the titration because we added 23 milliliters of our sodium hydroxide. We would then obviously know we should at least do an ice table of that reaction that's going to occur. We also should know, since we've been talking about titration, we should be doing this in moles. So we want the moles of each of those. So that's going to be 0.025 times 0.1. And that's going to give us 0.0025 moles for our acetic acid. We have enough information, obviously, here to get our moles of sodium hydroxide, 0.023 times 0.1, 0.0023 moles of this guy, nobody of this guy. Any questions on how I got the moles there? So volume times molarity, again, making sure you convert to liters in this case, because you do need to do that. Now, we've already established this is a weak acid, strong base titration, which is a good first step in understanding maybe, what you should be doing. But even if you got to this part and you really weren't sure if you were before the equivalence point or after the equivalence point, you could use your ice table to figure that out. So again, this is what I'm starting with. That is what I'm adding. And clearly I have less moles of what I'm adding to what I started with. So that tells me I am definitely before the equivalence point, which is another very good piece of information to know, because right now, without me telling you, you should know what type of problem this is. I won't say it right now, but we will continue on and make sure you hopefully got it right. By the way, if you didn't want to do that, even before you did the calculation, this is a 1-to-1 relationship. So if you did your M1 V1 equals M2 V2 and plugged your numbers of 25 milliliters and 0.1 molar equals 0.1 molar, the V2 that you would get would be 25 milliliters to reach the equivalence point. And clearly you've only added 23. So that also tells you you're before the equivalence point, if you wanted to figure it out that way as well. Any questions on any of those reasonings here that I just did? All right, so because we are not at the equivalence point, we're before the equivalence point, we do know that this guy here is going to be our limiting reagent and also the change that we would expect to occur. And that means when we do reach equilibrium here, we will end up with 0.0025 minus 0.0023. That's a lot of zeros there, but 0.0020 moles, nothing on that guy, and 0.0023 moles. Any questions on the ice table so far? Okay. At this point, we do want to convert back to volume. Remember that this calculation I did up here was to reach the equivalence point. But our total volume in this particular problem is we did start with 25 of the acid. We added 23 milliliters of the base. That's a lot of math there, but I can go with 48 milliliters. That means that we would want to divide each of these by 0.048 liters to make sure we do get molarity. That's going to give us 0.002, 0.048. That looks like we got like a 0.00417, we'll call it, and 0.0023, 0.048. This particular case here gets a 0.0479 molar in that particular case. All right, so at this point, again, what you have left, if you're not sure what's going on, is you have acetic acid, you have sodium acetate, and you hopefully should see that those two are related to each other. And this is a buffer situation, which is what you should have known from those two pieces of information before you actually did any of the calculation there. So again, this is why sort of thinking about what you're doing in these problems are important. So you can make sure when you get down here, you actually do end up with what you should have at this point. You didn't end up with something weird going on. Any questions at this part? Because this is a buffer, you do have the option of another ice table, but I'm personally going to go into the Henderson-Hasselbalch equation. And that means we have 4.74, which is our pKa value that we've used before. The other important thing is, as we talked about last time, this is our base. So that guy should go up on top. And this is our acid, because the simple answer is this is acetic acid, which would make sense. That would be our acid. Remember, the base, a lot of times in these problems, will have some type of one less hydrogen and some type of spectator ion hanging out there. And that's, again, a good way you can figure that out as well. And if we do all that good stuff there, it looks like perhaps we do end up with a pH. Call it 5.80 at this particular point. Any questions on that there? Where any of the numbers came from, why I did anything? Any questions? And just to see how we did. So on this one example, where the numbers came from, by the way, the numbers came from this particular type problem. So we're at 23, which is here. And our 5.8 does fall between these two numbers. So that's good, at least. So we probably did something right. By the way, the numbers you see on those tables are specific for like the problem we just did here, not other problems. So those pH values won't always be the right ones for other titrations. Other questions on that?
So does that help us find out like where we're at on the graph with answering that problem?
Yeah, so literally you can figure out where you're at. And if you're not sure where you're at and you're doing a titration problem, sometimes the easiest way to figure out really sort of where you're at is to simply just to do this part of the ice table in moles and understand, where everything is. So this is obviously in the beaker where we're adding stuff to. This is obviously what we're adding. And just doing a simple comparison of moles at this point by just doing that first little bit of the calculation, if you're not 100% sure where you're at, and comparing these two numbers here. And always in a titration, you really got kind of 4 parts, right? So before you start, obviously you would have no moles of the base. The part before the equivalence point, before you reach that equivalence point, in the case of this type of titration, the moles of the base will be less than the moles of the acid, and you have more acid than base. When you reach the equivalence point, the moles of the acid will equal the moles of the base. And when you're past the equivalence point, at that point in this type of titration, the moles of the base will be greater than the moles of the acid. So you only really, if you want to sort of figure it out before you get too far, which is really a good idea to kind of know where you're at, because they won't say, hey, you're like before the equivalence point, or they won't say you're after the equivalence point. They might just tell you you're at the equivalence point in certain problems, but they really won't give you a lot of location, like where you're at. So just by simply just doing that very first initial line and really just comparing these two numbers, and either you're like here, or here. And in the case here, we see the moles of the base is less than the acid, which tells us we're definitely before the equivalence point. So that's what you could use really to determine where you're at. And by knowing that in this type of titration, I know really I should end up in a buffer situation at that point, which is exactly what I ended up with. So these are ways that you want to kind of think about these calculations and not just do the calculations, just to make sure that when you're done, you do end up where you should be and what you expect to happen. So by just simply looking at those two numbers and understanding the titration before, again, I finished the calculation or got anywhere, I should really know kind of where I'm at. I should know A, I'm before the equivalence point. B, I should end up with a buffer. And by the way, I probably know that in most cases that buffer is probably going to be relatively acidic at that point. And I have a pretty good understanding of where I should end up, which is always good, because I've seen people go through these problems and just like, okay, I know I got to convert things to moles. I'm going to throw it into an ice table. And then it's like, I'm not really sure what I should be doing next. So sort of knowing where you're going, right, is always good. That's what they say, that where you're going places, right? Driving somewhere, it's always good to kind of know where you're going rather than, well, I'll hop on the freeway, hope for the best, get off of this off ramp. This road looks nice, there's a nice drive-through restaurant or something, we'll go there, so it's good to kind of know where you're going so you don't get so lost in these problems. And it's good to know that up front. Other questions? All right, any questions on then this type of titration, which obviously, as you can see, slightly different than the previous type of titration that we spoke about. Okay, so the next type of titration we're going to talk about is a little bit different, and it's actually a strong acid and a weak base titration. So the setup here is also a little bit different than we've been talking about in terms of, where everybody's at. So in this particular case here, the setup is we actually have up in the burette is our strong acid. So we're actually adding acid in this case. We're starting on the bottom with a weak base. So a little bit different. We're actually adding the acid to the base here. You will also look at the curve and see it's a little bit different. It's sort of upside down, and we'll talk why that is here. So for example, if we had a strong acid like hydrochloric acid and we added it to NH3, which is a weak base, we would get something like NH4Cl, ammonium chloride. This is a weak base. Obviously, this is a strong acid in this particular case. So let's talk about why this curve sort of looks like this and what happens at each of these spots. Well, let's just start right there at number 1, like we've been doing. We'll look at the same 4 sort of spots. So number 1 here, we have not added any acid to this. So what is going to happen here at that first spot? So before we add acid in this case, the only thing we got in that beaker or flask is a weak base, which means we need to do a weak base problem, which means we take something like NH3 in this case, which is the weak base. We would react it obviously with water. We're going to get it to accept that H plus because it's acting as a base. That's going to make NH4 plus and OH minus here, right? Which also makes sense because, again, it is a base. So this is a nice table where you use the molarity. These guys are going to be zeros. We're going to do some minus x's, plus x's, plus x's, and we're going to end up with m minus x, x, and x. This is a KB problem, right? Which means you would use a KB problem, obviously solve for x. Also reminding yourself that when you do solve for x, it is actually the hydroxide concentration here. And that means, again, here we could get to our POH and then to our pH at this point. So again, a little bit different than the previous one we just talked about, but kind of similar. The last one was a weak acid we started with. This one is a weak base. Also, why? We're actually starting at a higher pH here because we're pretty much starting with a base. So we're actually going to lower the pH as we do this titration, right? So as we drop this guy in there, we're going to start lowering that pH and actually become more acidic, which is what we see here as we go left to right on this graph. Any questions on that first part? All right, so continuing on like we've been doing, what happens there? What happens there when we start the titration? Our first drop of HCl in this case, all the way down to right there till we reach the equivalence point. Again, we'll call this number 2 like we've been doing. So let's take a look at sort of what happens in that situation. So number 2 would be before the equivalence point. So clearly we are going to have a reaction, and that reaction is what we've been talking about. So NH3 plus some HCl. Maybe I'll learn to write. There we go. Get some ammonium chloride. And same idea, you want to think about this is what I'm starting with in this case. This is what I'm adding. So initially, again, we want to do moles here. So I'm going to use my same made up value of 4 moles that we used before. And again, knowing that information of the equivalence point is moles of acid equals moles of base, this tells us that we definitely should have less moles of the HCl in this case. So again, I'll use my made up number of 2 and 0. Change in this case going to be our limiting reagent, which is the HCl. And that is going to get us 2 moles of this guy, 0 of this guy, and 2 moles of this guy. At this point, we want to convert back to molarity like we've done before using the total volume there. And again, if you're not sure what is going on at this point, take a look at your ice table to help you. We do have NH3 there, and we have NH4Cl. These two things are related to each other. A reminder that NH4Cl is NH4 plus and Cl minus. This guy and this guy are related to each other. That is actually a buffer at this point. So kind of similar to what we saw in the previous one, we're actually going to end up with a buffer, which means we could go into our pH is equal to our pKa plus the log of the base over the acid. Again, this being our base, this guy being our acid. And the important part though as well is it's still the pKa value when we use this. You probably have a Kb given to you in this problem. So you want to make sure you get to that pKa value. Again, a couple different ways you could get there. One relationship we talked about, pKa plus pKb equals 14. So that's one way you could do it. You could use Ka times Kw. I say that wrong. Ka times Kb equals Kw to get to your Ka value and then to your pKa value. So you could get there that way as well. You alternatively, as well as just like in the last one, if you don't want to do the Henderson-Hasselbalch, you could also do a nice table at this point as well. Any questions on that particular one there? So again, very similar here. We're going to need at least one ice table. Purpose of the ice table is to get your buffer components, and then you could go into the Henderson-Hasselbalch. And as you can see, most cases going to probably be fairly basic, maybe a little acidic as you get towards the equivalence point, but for the most part of it, we're going to have sort of a buffer region sort of happening there as we get through there. Any questions on that? We actually do see the same sort of situation as we approach the equivalence point. We see that vertical sort of drop in this case rather than rise in the pH because we are adding, in this case, a strong acid. Any questions on that? Okay, so as we've been doing, let's talk about number 3 here, which is the equivalence point. And at number 3 here, let us talk about what happens when we do reach the equivalence point in this titration. So number 3 here, at the equivalence point. And again, we will have our reaction of our NH3, our HCl, and NH4. I'll break it up here so maybe it'll be easier to see what's going on. Or you could keep it together in this particular case, your situation, whichever way you want to do it. Initially here, again, we're going to do moles. I'm going to use my made up 4 moles. But again, because we're at the equivalence point, we know we should have the exact same amount of HCl that's being added, right? And starting with here. So I know this number should be 4 moles. This would be 0. Change here again would be 4 moles. You can't really pick the wrong number. That means at equivalence, there's 0, 0, and 4 moles. Convert that guy back into molarity at this point. And what are we left with? Well, what we're left with is really this guy right here. we're left with this guy as well, but I ignored it because it is chloride, which means it's a neutral salt, not going to do anything. But this guy is a salt that will go through hydrolysis because it came from a weak base. So just like what we saw in the last titration, at this point, at the equivalence point, we actually should have a hydrolysis problem happening, where because this came from a weak base, this will be acting as an acid, which means it's actually going to donate its H plus over there. When it does so, just like we've seen before, it makes where it came from, and it makes H3O plus, which means before I even finish this calculation, I should know the pH should be acidic at this point because of this hydrolysis problem that's happening. Question on that? This would be an ice table where we would use obviously the molarity from above. From the first table, these guys would be zeros, and we would do some minus x's plus x, which means we would end up with and minus x, x and x. This is going to go into a Ka. Also, why it's important to write these right, because that should tell you you need a Ka value. Again, you probably have a Kb value at this point, so you need to do some kind of changing of that. Ka value will allow you to solve for x in this case. And when you do, that will be your H plus concentration, which means you could go directly into the pH at that point and get the pH. So very similar to the previous titration. The only difference is we're kind of going more acidic this way, as we're adding obviously a strong acid in this case. So when we get to the equivalence point, again, going to require two ice tables. First one for the concentration of the salt. Second one, a hydrolysis problem, just like we talked about earlier. Any questions at that point?
Didn't we find the Ka for like that previous one for number 2?
Yeah, so you might in this case, if you were given a problem where you did multiple parts along the way, you could at this point this could be like a standalone problem as well, where it might just ask you, what is the pH at the equivalence point? In that case, you probably would have just a Kb value. But if it was a problem where you did multiple parts along the way, especially, a part before the equivalence point, you might have the Ka value given to you. But again, if it was more of a standalone problem where they just said, hey, what is the pH at the equivalence point? And that's all they told you. They probably would only give you the Kb value in this one. So you wouldn't need to make sure that you do convert it. But you're right. If it was sort of a step-by-step sort of titration problem or something like that, you might actually have it at that point. Other questions? Okay. So now we're getting to the end here. Let's just finish out the last little bit of this titration curve here so we know what's going on. So just like before, the last little bit here would be obviously after the equivalence point to whenever you decide to stop at that point. So let's talk about what happens in sort of that fourth area of the curve here. So clearly we were just at the equivalence point, so you've got to be past it at that point. So number 4, you would be past the equivalence point. So much like all the other ones here, we will have that reaction that will occur. And again, I'll separate them again in this particular case so you can kind of see the differences what we got going on, or you can keep it together. So just like we've been doing, we will use moles. And again, I will use 4 moles of this guy, which is what I'm starting with. This is what I'm adding. And again, that knowledge and understanding of what's going on, since I am past the equivalence point, I need to have more moles of what I'm adding in this case, which again, I'll just make up as 6. Change got to be the smaller number so you don't get a negative. It's a simple way to remember that. And 0, 2 moles of this guy, and 4 moles of that guy. So like we've been doing, always very good practice to convert these guys back into molarity after you do that first ice table. Any questions on the ice table here? Again, looking at what we got left at this point, we have some HCl, we have some ammonium chloride, and again, we do have some of this, but I already know that's neutral, so that's not going to do anything for the pH. We also, hopefully, I hope you can recognize that these two things are definitely not related to each other. So the HCl is a strong acid, and this is also an acid like we were just talking about that will go through hydrolysis. But in comparisons of these two, much like what we did in the previous titration, out of the two of them, it is going to be that HCl that's going to really be the major contributor of H plus in that solution. Even though, again, that NH4 plus is reacting and producing H plus, but between the two, we're going to ignore the contribution of this guy at this point in the titration and look really at just the HCl, because as soon as you add it, it produces H plus immediately. It's going to be the major contributor there. So because of that is, again, a strong acid, that means that you would have the H plus concentration from it, and that means you could go right into the pH. So again, very similar to the previous one. At this point in the titration, you're really just dumping a lot of acid, and that means that you really just need to do one ice table. Really, the purpose of the ice table is to figure out what is the new concentration of your strong acid. And once you do that, you then could go into the pH equation and get the pH at this point. So this titration is very similar, the 4 parts, to the titration we just talked about previously. The only difference is in the last one, we're kind of going from basic to acidic. In this one, we're starting at basic and we're coming down to acidic type solutions. So they're kind of opposites of each other. One we build up, the other one we're starting up and coming back down because we're adding base in one case and acid in another. Question on this type of titration curve here. All right, so those are the 3 major titration curves that we're going to talk about in this class. You obviously need to be able to calculate the pH anywhere along any of these curves. And like I said before, sort of understanding the type of titration, where you are at in the titration, and knowing what should happen in terms of the calculation clearly makes calculations so much easier than trying to kind of just jump right into it and try to figure it out along the way. Any questions on anything we talked about today here in lecture? Okay,